Next, we have Dr. Maddalena Adorno. Dr. Maddalena Adorno is the co-founder and CEO of Dorian, a women-led and women-founded Stanford spin-out aimed at modulating epigenetic regulator of stem cell activity. In the past years, she has also been an instructor at Stanford Continuing Studies, teaching a course titled Lunging for Longevity. Welcome.
Thank you for the invitation. Coming here almost every year seems always more like a reunion of friends. And it's particularly nice to be in this session after the talk of Mike and the talk of Vittorio for two different reasons. I think Mike really told the story of senolytics, and they mentioned a paper of 2011 where they show the clearance of senescent cells. I think that paper changed my life, and I'm sure there are other people whose life was changed by that paper, because it's really when the real science of aging started becoming real and conspicuous, and so more and more energy were invested in this space. And the talk of Vittorio was very interesting because he was mentioning the importance of the epigenome and how we are immortal as a species because of the ability to modulate the epigenetic landscape. And he was also mentioning how nature shows us often answers to the problem that we are asking ourselves. And the story that I'm going to show today also shows another example where nature is teaching us something. And I will talk a bit more about what Down syndrome has been teaching us. And the story started at Stanford more than a decade ago, and then was spun off in my company, Dorian Therapeutics, that is also here based in the Bay Area. And so we talked about senescence, and another trait important for the aging process is actually stem cell exhaustion. And these two things always go together. So there is this paper published by Dos Santos in 2023, where you see that when the markers of senescence increase, the marker of stem cell goes down. So you can really separate one process from the other. And one important factor that links the two activities is actually the epigenetic remodeling itself. So often when we think about epigenome, we think about methylation and acetylation. But another important process in the epigenetic landscape is actually ubiquitination. And the ubiquitination enzymes are actually key players during the aging process. And this has been shown also in worms, where they show that if you actually block the activity of DABs, the ubiquitination enzyme, you see an increase in lifespan of this animal. And just in the last 10 years, basically, DABs are becoming very interesting targets in the space of age-related diseases. There is USP30, for example, that is a DAB that has been recently explored by Mission Therapeutics, involved in mitochondria functionality. And today we are going to talk a bit more about USP16, that is one of the DAB that we are focusing on at Dorian. But this space is pretty new. Just less than 10 years ago, DAB were considered impossible targets from a pharmacological point of view. So it was very hard to develop drugs for this. But we and others have been successful in developing a small molecule for this indication. And again, at Dorian, one of the main targets that we focus on is USP16, that is a deubiquitination enzyme that actually modulates the chromatin. And by doing so, by removing ubiquitin from the histone, it actually antagonizes the activity of PRC1. You have been hearing in Vittorio's talk, and probably Andrea, I don't know if is gonna talk also about this in some other talks, but PRC1 and PRC2 are some of the very important sites that are regulating activity and the epigenetic landscape. So how did we get to the identification of USP16? So here is where the story becomes very interesting. USP16 is located in chromosome 21. and trisomy of chromosome 21 results actually in Down syndrome. And if we look more carefully at the Down syndrome phenotype, what we see is that it's a clear overall situation of accelerated aging. So from a clinical point of view, we see skin aging, hair loss, osteoporosis, diabetes, et cetera, et cetera. After we published our paper in 2013, it has also been extensively proven that epigenetic clocks are accelerated in people with Down syndrome. And on top of this, you see clearly the effect on senescence, with an increase in senescence in Down syndrome and a strong decrease in stem cell number and functionality. So we have an epigenetic change, we have an aging change, we have a stem cell change, and we have a senescence change. For us, this was the perfect system where to actually do reverse engineering to understand what is causing this accelerated aging. And if we understand this mechanism of accelerated aging, we can actually also hack it. And what we saw is also trisomy 21 is also associated with chronic autoinflammation, that it's another very crucial aspect of aging. Very interesting also that USP16 levels are genetically overexpressed in Down syndrome, but a high level of USP16 are also associated with natural aging and with several diseases, from fibrosis, osteoarthritis, and a number of autoimmune diseases. And just by this process of reverse engineering, what we understood is that the gene on chromosome 21 that was responsible for this accelerated aging was USP16, the DAB that I was mentioning before. And just modifying uniquely, just a pinpoint modification of USP16 extra copy and take it back to normal, even in a context of Down syndrome, you have that the stem cells start working again and the senescence goes back to more normal level. And this is not only a change in cells, but we really see that in different pathology, this has a very profound effect. So Alzheimer's disease is improved, osteoporosis is improved, and metabolic syndrome is improved. So again, we realized that we stumbled upon a key regulator of aging. And one of the reasons that we are among the first to identify USP16 between these is that, again, if you don't work with primary cells, if you work with cell line, you are actually unable to pinpoint this mechanism of action. What's also interesting is that, again, if you forget about Down syndrome, you go from normal level of USP16 to low level of USP16. What you observe is that, first of all, these mice are completely fine, but also that during aging, they start developing hyperfunctionality. So they are aging less, basically. It's the entire paradigm of actually health span. We didn't do longevity study with these mice, but what we see is a clear improvement in health span. That, from a personal point of view, it's also what, for me, is more important in this. And we said that this is mediated by actually modulating the chromatin, and at the PRC1 sites, really changing the accessibility to region of the DNA that are controlling stem cell activity and senescence. So this was the basis of all our work. So what we did at Dorian is actually develop a small molecule to target USP16. So we did a lot of activity in this. We are the first people to have actually a crystal structure on this target. And we developed a covalent catalytic inhibitor that is highly potent and highly selective. So again, it's highly selective, it's orally bioavailable, it's highly potent. Being a covalent compound also has some properties that you don't see in normal small molecule. Because what you see is that it disappeared from the blood very quickly, but the activity remains after the disappearance of the drug. So this allows to have a very different profile from a drug that needs to be in the blood to work. Actually, this binds right away and it has sustained activity during time. And during the last few years, we have been exploring a number of indications where we looked at the activity of USP16 inhibitor. So some of them have been validated from a genetic point of view, some of them have been validated with small molecule. And also we have been proven that also systemic treatment with the drug doesn't present a strong safety concern. So it's actually possible to build a pipeline in a pill. And I want to show you a couple of examples of what we are working on. The first indication that we started working on several years ago is actually knee osteoarthritis. That is a very difficult indication when it comes to clinical development. So this is a big challenge in this space. We also have a $4 million grant from NIH to support the development of this program. And initially, our idea, kind of in line also with what Unity did in the past, is that since you can do local treatment with a small molecule, we can also reduce the systemic exposure to our drug. But also, just recently, we realized that our drug penetrates very well in the knee. So we can also think about a systemic treatment with our drug, since the safety profile so far has not shown any major problem. And in the knee cells, so in chondrocyte, the cells that generate the matrix of the knee, what we see is that, again, we have an epigenetic change that we can measure by histone ubiquitination, and a change in level of senescence. But what's also very interesting, and again, this looks a lot like the slide that Vittorio was showing before, is regarding the expression profile of these cells. So here again, we are talking about modifying one single gene that though changes the opening and closing of the chromatin, and by doing so regulates multiple genes at the same time. So what we see is that if we take chondrocytes from healthy donors and we use our drug, nothing major changes. So also from a safety profile, we are not doing much to these cells. But if we take osteoarthritis chondrocytes and we treat them for 10 days with our drug, now the expression profile looks like the expression profile of healthy chondrocytes. So we are doing a massive work in reactivating normal pathway of expression of these cells. And this does not affect only chondrocyte, but also the stem cell of the knee, the mesenchymal stem cell are expressed. You see again expression, for example, of SOX9. That is one important marker on this. And the chondrocyte generated by these MSCs are more effective in generate matrix. What does it mean when we move to animal model? Well, we use this surgery model of osteoarthritis. It's a medial meniscal tear, MMT, and performed in rat. And as you can see from the graph on the right, these animals, after the surgery, they are in high level of pain. So the pain threshold is, of course, inversely correlated with the pain itself. But what you see is that when you block USP16, in actually 2 weeks, you have basically a restoration of normal level of pain. That it's kind of a strong effect in this system. And this is accompanied by a reduction in senescence, catabolism, and an improvement in cartilage. And if you look at the histology score, you see that the histology is strongly improved, as well as the level of VEGF in the synovial fluid. Another indication where we have been working a lot, that is now our leading indication at Dorian, is actually lung fibrosis. And there are a number of programs in lung fibrosis all around the world. And for us, it's very interesting to see how several things that are important for the pathology are actually regulated by USP16. And so we think we have a shot in having really a different way of treating the disease. Another thing that for us is very interesting is that in this paper from Dos Santos, they looked at in what tissue you have the biggest decrease in stem cell activity during time. And you can see that in lung, basically ranks at the first position in this. You have a strong loss of stem cell in the lung. And on the right, you can see that also in IPF, the epithelial stem cell, the 82 cells are actually depleted in IPF patients using different markers. So what we saw is that when we treat with our drug, what we see is a strong decline in the modulation of profibrotic marker. And the same goes for antifibrotic marker. And we have a similar effect to C21 Vicor, that is a drug that is currently very advanced in clinical trial, that is an activator of stem cell. And also alpha-SMA, it's regulated actually by DT201B, showing how strong of an effect we have in fibrosis in this model. This basically results in changes in vivo in models of lung fibrosis. So in this case, we use the bleomycin model, but we have also other models of inflammatory-based IPF. And what we see is that it doesn't matter how we do the treatment. If we do a preventative kind of treatment, of therapeutic treatment, during time we see, in 2 weeks, we see a strong improvement in the fibrotic lesion. And so we want to move this forward towards the clinic. And so I show you these two indications. I think it's very interesting to see how when you hack a mechanism of aging, you can really think about extending your pipeline from one indication to several possible things. So just to finish, I would like to thank you, the Dorian's team, and investors and supporters that supported us during these years. And I'm happy to take questions now or during coffee.
Very cool, as always. So, just a speculation. So you show that there are, of course, cell type specific effects. No, the RNA-seq is clear. When you have like a wild type cartilage, you don't have effect. Otherwise, when you have like the disease control, there is a huge change. But also inflammation seems to be like, should be a good hypothesis of an effect. So I was wondering, are you still thinking, or you are planning to actually administer the complex to wild-type mice or to wild-type individual to see if the anti-inflammatory effect that you might have can like lead to a healthier life without working with a pathological condition, which is easy to measure, of course, and more relevant, but I'm thinking about the overall inflammation, if that makes sense.
Yeah. So again, it's always easy to get this data in a pathological situation, but we did a lot of studies actually in autoimmune situation. So we took, for example, models of lupus, and we see in lupus, in models of mice model that develop spontaneous lupus, the effect of the treatment during time. And we saw very beautiful reduction in the inflammation there. The other thing that we did is we worked a lot with the T cells and driving exhaustion. You heard it before, I think. So again, what's beautiful is that exhaustion of T cells, it's an event that for us comes after the aging markers come up. So first you see the aging marker come up, and then you see the exhaustion markers come up. And what we have seen is that actually modulating USP16 is a very effective way to keep the T cells younger and more effective. So we tried this with CAR T cells, and it works. We tried with non-CAR T cells, and it works as well. We tried with old cells, and we tried with young cells.
Hello, thanks for the interesting talk. And I saw that you are trying do a trial on ulcerative colitis. But why? Have you think also you discarded the Crohn's disease? But looking at the results on fibrosis, pulmonary fibrosis, I think could be interesting as well in Crohn's disease. No? Thanks.
Yeah, exactly. It's, so the entire autoimmune bucket for us is very relevant. We see a very strong effect on the immune system. And again, we are not the only people that are working on USP16. And other groups have shown in vivo the effect of USP16 downregulation in the immune system on diseases like ulcerative colitis and Crohn's diseases. So this is something that we partially reproduce this data in-house, but it's very interesting to go in that direction. There, it's all about indication prioritization and chances of success with models.
Hi, thank you for the great talk. My question is, are you looking into the skin in terms of fibrosis like scleroderma and morphea and things like that, that maybe be an easier target?
Yeah, so we actually ran experiments in scleroderma as well, but with systemic delivery of our drug. So with systemic delivery, we don't have enough penetration in the skin to actually make a difference on that. But what's interesting is that, as you probably know, the model of skin scleroderma develops also secondary lung fibrosis. So what we see is that we don't have an effect on the skin, but the lung fibrosis driven by scleroderma is actually improved. I think it's a very cool data. Thank you.